Hello! In this video, I want to explain what we mean when we state that two random variables are correlated. This video and the following exercises are intended to be a first pass at this important topic. We will return to this topic and discuss it in more detail next semester. Furthermore, if you continue on studying statistics, whole modules will be devoted to the study of correlation. By the end of this week, therefore, you should have a sense of what correlation means and why it is important, but you will by no means have a complete understanding of this topic. By means of an introduction to correlation, let's review some ideas that were introduced a number of weeks ago. When we studied variance and the method of least squares in week 5, we introduced the following framework for thinking about random variables. We said that the random variable capital X could be written as a sum of the true expectation of the random variable and a random variable which we call delta that could be positive or negative, but that had expectation 0. We visualized this decomposition of the random variable capital X as shown here. We drew the real axis as a horizontal line and noted that the expectation of the random variable was a particular fixed scalar that always appeared at a particular point on the real axis, as shown here. Delta was then the difference between the true value of the random variable, the blue point, and the expectation. Furthermore, as the random variable can take any of a number of values on the real axis, it can appear to the right of the expectation, as shown here, or to the left, as shown here. If the true value of the random variable is to the left of the expectation, however, then delta is negative. This way of thinking about random variables gave us an idea for estimating the expectation of the random variable. We plotted a graph of the various estimates that we got for the random variable against a numerical index as shown here. We then drew a red horizontal line to indicate the expectation and green arrows to indicate all the various delta values. These delta values indicate the part of the random variable that is actually random, the rest being predictable based on the value of the expectation. When we did this, we introduced the following expression and showed how this quantity would be equal to the average of the square of all the delta random variables. We insert this expression into here, and through cancellation we see that this is the case, that this expression is equal to an estimator for the second moment of the distribution of delta. The introduction of this quantity led us to the method of least squares and a way of estimating the parameters of our distribution. Now, with all that in mind, let's suppose that we draw a graph of the random variable capital Y against the random variable capital X as shown here. The blue circles here indicate a series of samples that we have taken from the joint distribution. You have no doubt learned at school that we can draw a line of best fit through these data points as shown here. When you do so, you are assuming that the random variable capital Y is a linear function of the random variable X as shown by the equation at the top of the slide. Like any linear function, alpha in this expression is the intercept between the red straight line and the y-axis, while beta is the gradient of the line, as indicated here. What you perhaps haven't learnt when you did this at school is that when we plot such lines of best fit, we can write a delta after the linear part of this function and thus account for the remaining randomness in the value of the random variable, i.e. the randomness in y that is not explicitly correlated with the value of capital X, as shown here. Much as was the case when we considered how least squares works for determining the expectation, delta here is a random variable with an expectation of 0 that can be positive or negative. Delta tells us the difference between the true value of the random variable and the value that would be predicted for the random variables if we assumed that y was purely a linear function of x. So the green arrows here indicate all the delta values. When we say that the random variable capital Y is linearly correlated with the random variable capital X, we are stating that we can get a reasonably accurate estimate for the value of Y by computing a linear function of the random variable capital X. In other words, the expectation of the square of the random variable delta in the expression shown at the top of the slide is relatively small. How do we go about calculating the values of alpha and beta in this expression though? Well, notice that if we have multiple estimates of the random variables x and y, we can calculate the average that is shown here. This expression is similar to the expression that we used in the method of least squares when we calculated our estimator for the expectation of the distribution. Furthermore, notice that if we substitute the expression for y in place of the yi here, this expression reduces to an estimate for the average of the square of the random variable delta, just as the similar expression that we used in the method of least squares for determining estimators for the parameters of the distribution did. To see how this idea can be used to estimate the alpha parameter of the distribution, I want you to watch the following movie. The black points in the panel on the left here indicate a series of samples that I have taken from the joint distribution of the random variables x and y. During the movie, a green line will appear on the panel on the right. The green line indicates the graph of the function x plus alpha for various values of the parameter alpha. During the movie, a green point will also appear in the panel on the right. The x-coordinate of this green point is the value of alpha for the green line that is displayed in the left panel. The y-coordinate of this point is equal to the expression that is shown in the y-axis label. In this expression, the sum runs over all the samples from the distributions of x and y that was taken. Here is the movie. What you should see is that the function that is displayed on the y-axis of the graph is a quadratic with a minimum when the green line is centered in the cloud of sampled points. Let's now consider what happens when we generate a similar movie in which the beta parameter is adjusted instead of alpha. Once again, the black points in the panel on the left here indicate a series of samples that I've taken from the joint distribution of the random variables x and y. Furthermore, a green line will appear in the panel on the left as the movie plays. The green point here The green line indicates the graph of the function beta x for various values of the parameter beta. The green point in the panel on the right has the value of beta as its x-coordinate. The value of y is once again equal to the function of the sample points that is given in the y-axis label. Here is the movie. What you will see once again is that the function that is displayed on the right is a quadratic with a minimum that appears when the green line is centered on the cloud of points in the left panel. What has been shown on the y-axis of the panel on the right of these graphs is the function of the parameters alpha and beta that was introduced in the last but one slide and that is shown at the top of this slide once more. As was discussed on the previous but one slide, this expression is an estimate for the second moment of the random variable delta. In other words, it's the average of the square of the delta values. Just as we did when we used least squares to find the parameters of the distribution, we are going to find the parameters alpha and beta by minimizing this estimate of the second moment of delta. As we have seen from the movies, there should be a nice single minimum in this function of alpha and beta. If we call this expression s squared, we are going to take the following pair of partial derivatives. Notice we need to take partial derivatives here rather than total derivatives, as s squared is a function of two parameters, alpha and beta. As we are looking for a minimum, we are then going to set these two partial derivatives equal to 0. Having calculated partial derivatives and set them to 0, we can rewrite these expressions shown here as follows. We now have two simultaneous equations with two unknowns, alpha and beta, to solve. To solve them, we will take the first of these expressions and we will multiply it by 1 over n, multiplied by the sum over all n, as shown here. Notice that the first term in the resulting expression is equal to the first term in the expression immediately above it. Notice furthermore that these are the only terms in these two expressions that are dependent on alpha. If we thus subtract the expression we just obtained by doing this multiplication from the expression above, we arrive at the following expression that contains only beta. Rearranging this gives us the following estimator for beta. To get the estimator for alpha, notice that if we divide all terms in this first expression by n, the n here cancels, while the sum over all xi turns into an estimator for the mean xi of x, and the sum here turns into the sample mean for the random variable y. Once we have evaluated beta, we can thus calculate alpha by taking the following simple functions of the sample means of the two variables. Notice that alpha and beta are estimators for the parameters of the linear function and are thus random. In other words, these quantities, like any other random variables, are samples from some distribution, which, if we report estimates of these quantities in a paper, we should endeavour to characterize so as to make our work reproducible. We will leave a discussion of the distributions of alpha and beta to a later week, however, now just finish the video here. Thanks for your attention, and as always, good luck with the exercises that follow.